Yesterday, we saw that this theory that describes the low energy limit of a stack of D3 branes, which is n equals 4 super Young-Mills, is conformal. So let me recall a few things. That local gauge invariant operators in n equals 4 super Young-Mills include such objects, which are traces of a bunch of letters that form a word. The word I indicate with this A. A would be the sequence, a choice of which fields to use. So A here would be a word, where these letters, chi1, chi2, etc., are all at the same position in space-time. Now, just because this is a trace, is a product of fields, so in the double line notation, we would indicate it like this. It's a product of fields. This keeps track of the indices, how the indices are multiplied. Of course, now it's not just a single matrix, so I need to keep track of who is at each position. So I need to write some chi1, chi2, chi3, or some notation to indicate what I'm doing here. Or I could also draw it like this, but I keep in mind that even though I drew it like a big picture, this is all at the same position x. Right? So don't be confused. This is all just a point. I just blew up to see the index where it is. And this, of course, looks like a closed string, right? This just looks like a loop where I have a bunch of string bits, if you want, all this product of fields. And the picture would be that if we start doing correlation functions of these operators, this would look like, from a topology point of view, as correlation function of closed strings. Right? If you do a 4-point function or a 3-point function, you will draw these planar surfaces that look like the interaction of 3 closed strings. At least as far as pictures goes, that's true. Now, these operators, a cute way of writing any field of n equals 4 was using these creation operators. You had these oscillators, A and B and C, and that's enough. With these oscillators, A carries index alpha of SU2, C carries index A of SU4, and B, we also have B, that carries index alpha dot of SU2. And together, A, B, and C, you can construct any operator that has a given number of R charge indices, A, B, C, and a given number of SU2 indices, alpha, beta, gamma, and a given number of SU2 bar indices, alpha dot, beta dot, etc. And here are all the operators you could construct. You could construct any number of covariant derivatives that are a bunch of A dagger times B dagger to the power k. And then you could construct, they could act on F, on psi, on phi, on psi bar, or on F bar. And then you would have this possibility for the various oscillators. One operator that was particularly nice was this one that we constructed. You see that this is an object that is in the same representation as trace of z square. Why? Because both are symmetric traceless. So from the point of view, they are just rotation, SU4 rotations of each other. Right? I can go from this to this by an SU4 transformation. How do we see it's traceless? You see that this object, it's symmetric because there are just two fields, so it's by definition symmetric. And if I take the trace, which in SU4 language means I contract with this epsilon tensor, here I get the contraction, and here epsilon with epsilon, there are 24 options, so 1 over 4 factorial kills those 24 options, and I get contraction minus contraction, so it's traceless. So it's traceless, it's symmetric, so it's in the same representation of this guy that is also traceless and symmetric. And being traceless and symmetric and having maximal R charge implied that this operator were killed by some supersymmetries. They were therefore in shorter representations. They can't move, and they need to stay in shorter representations. So delta needs to stay equal to j plus 0. Because delta equal to j was the condition that you are in a short representation. And so this operator has dimension 2. You act with a bunch of q's. I wrote schematically there q to the 4. You get f squared, that therefore has dimension 4 because each q raises by 1/2. But this guy, by supersymmetry, is related to the Lagrangian. In other words, all terms in the Lagrangian, you can go from one to the other by supersymmetry. And so the Lagrangian needs to have dimension 4. And therefore, this coupling that multiplies the Lagrangian density has dimension 0, and the beta function is just 0. And so n equals 4 is a fully conformal theory. Okay. Now what we do today, what we are going to do today is try to think of these closed strings, these operators OA, and start studying correlation functions. Start see what is the physics, what happens in the n equals 4 supreme mills if I take two such words, OA at position X and OB at position Y. That's what we want to do. Okay. Now, this operator has classical dimension equal to, okay, this has some classical dimension, let me call it delta A, that's going to be the same as the classical dimension delta B. Now, to be concrete, let's choose the following operators. Let's say that chi A are equal to operators that are made out of the scalars only. So this A stands for a sequence trace phi m1 phi mj. So A stands for that sequence m1 up to mj. Then these operators here have classical dimension equal to j. Do you agree? So they will have classical dimension equal to j. And now what we are going to do is we are going to compute their correlation function. So this operator is, if I draw it in our double line notation, something like this, where here I have phi 1, here I have phi 2, and here I have phi j. And this would be my operator OA. And OB that I contract with is a similar operator. Sorry, I wrote 1, I meant phi m1. Phi 2, it's phi m2. It will be one of the 6 scalars. And phi j, phi mj. And upstairs, I have OB that would have 1, 2, 3, 4, 5, 6. Also 6 fields. Otherwise, I cannot contract. 3, 4, 1, 2, 3, 4, 5, 6. And to leading order, all we do in perturbation theory is contract these fields. Right? Now, because I contract these fields, I have here a phi n1, a phi nj, and because we just contract them, we get that this diagram here would be, there will be a Kronecker delta that says that m1 needs to be equal to n1, m2 needs to be equal to n2, delta, mj needs to be equal to nj, and then there would be a propagator. There is some overall normalization. It's not very important, but okay, we can write it. G squared to the power of number of propagators, j. There are some loops of n that we draw here. One loop here, one loop here, one loop here. So j loops of n to the power j, right? There's one loop outside as well. So there are n loops. I draw like this. And then each propagator is 1 over x minus y to the power square. So there are j propagators to the power 2j. And so this thing here, I can write as saying that the word A needs to be equal to the word B. Maybe I can put them both downstairs. A and B need to be equal. And that would be what we will get.
Question.
Yes.
This might be a silly question, but like, why don't we deal with permutations between N1 and M2?
Okay. So now, here, notice that by planarity, the lines need to contract directly up. So what we could do, what we cannot do, is contract this leg with this leg here. We cannot just swap and connect this one with this one here, because to do it, we'd have to pass by the other legs. And so by planarity, the lines need to connect directly up to up. Right? Now they could all rotate here, right? They could all rotate, but since we are dealing with a trace, the state here should be cyclic, and so there should be no difference in rotation. And so we don't need to assume this rotation. Okay. Right? Now, and so planarity, note that this structure here is crucial. So here, what we are doing is studying the large n limit, and we are very strongly assuming planarity. We are using planarity to say that this is what we get at large n. Right? So again, this diagram where the legs would do something like this, and then the other ones would contract like this. This would also exist, but it would be much suppressed in n if I do something like this. Right? So this diagram is much smaller than the planar one. It has less powers of n. And so planarity, what it's giving you, if you think of this as the cylinder of the string, planarity gives you locality on the string. Are there two L's or two T's? Local, is it okay? Locality? Yeah? Okay. So planarity gives you locality, right? Things cannot on the string interact far away, right? There is some notion of things that are nearby, they can interact, but not things far away, right? So it gives you locality on the string surface, which is the string worldsheet.
Here we are contracting things like in Fick's theorem we are contracting fields. So why not the same operator with OA contract with the phi with phi in A itself? Why it has to go to
so operators in quantum field theory, when we draw OA, we never allow for contractions between the same field. That we never do. So that when we renormalize the operator, typically we use some notation like this when we write the operator. So in other words, in this OA, if you want to keep in track that you should not do self-contractions, those would be divergent, right? A propagator between the operator and itself is 1/0. Sometimes we put some dots like this to indicate these are really composite operators. So a composite operator is different from starting with two operators. There you would contract and then joining. In a composite operator, you remove self-contraction. You don't do that. And so this object is equal to this at what we call tree level without loops. Now, what happens at one loop? So we conclude that the propagator OA OB equal, there is some overall power of the coupling, lambda to the j. There is some propagators, x minus y to the 2j times delta EB. That's what we got so far. Now at loop level, several things start happening. So now at one loop, let's draw what could happen at one loop. So again, we have our operator. And here we have the operator in the bottom. And at one loop, it means we are going to start using the vertices of n equals 4. Right? So we are going to use the vertex once or twice, right? We are not going to, it's one loop. Right? So we are going to bring down a quartic vertex, or maybe bring down 2 cubic vertices, but that's it. And because of planarity, things are going to happen somewhere here in the middle, say, but then here, far away, we still just contract. So there is a part that by planarity, again, nothing special must happen. Then let's say things will happen here, and so here nothing will happen. So by planarity, things are always localized in some small region. Now let's draw what could happen in this region. Well, we have a phi to the 4 coupling there, right? Phi, 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 phi. Right? And so they could couple here. We could have a 4-point vertex here. This comes from the commutator that's there. That's the only term the only interaction term I wrote. Actually, not the only one, but let's draw. So this is one possibility. Now there is another one that there is another interaction written here. This is one of them. This is done. There is another one. So where is it? Here. So what is it? What kind of interaction is it? If I draw it graphically.
A to phi 2.
Sorry?
A to phi 2. Something should come from outside.
So there are two types of there are two possibilities here, right? That involve the gauge field. What's the simplest one? How many phis do you have? And how many a's? How many gauge fields and how many phis? Here. There are two possibilities, right? When you write a covariant derivative square. Either you have 2 phis and 2 a's, or 2 phis and 1a, right? There is a cubic coupling and a quartic coupling, right? So, for example, a diagram we could have is also for example, I don't know, let's a cubic, a gluon. I'm drawing the gluon wiggly, but double line. Like this. That's one possibility, another possibility. Right? Another one is instead of this wiggly line connecting one line to the other, I could have the wiggly line could just connect with the same line. I could throw a glue and then catch it later. Really? And so, and there are more. Maybe I can just focus on this line. If I just focus on this line, I could have, for example, there is this Yukawa coupling that two fermions can couple to the boson. And so we could have, for example, in that line, something like this, where this dashed line now is a fermions, are fermions. And the dot, dot, dot here, dot, dot, dot here. I'm just representing this line here. The rest is the same. Plus, there could be perhaps a few more options. Now, this is a lot of diagrams, right?
Where is the case that we have 2a, 2 phi?
Sorry?
Where is the case that we have a to the power 2 and phi to the power 2?
I did not draw, so it's here in the dot, dot, dot. Let's draw it. So it would be something like this. And then there would be two gluons getting out here. Right? And they do a bubble. And the other lines do nothing, right? You agree? Now, notice now something very important, which is that gluons don't carry SU4 charge. So whatever these diagrams give, if this index here, if here I have phi m, here after the gluon interacts, I must also have phi m. The gluon cannot change the SU4 charge. The gluon is neutral, right? Doesn't carry any, when in the coupling there's no, right? There is phi m, and the d mu doesn't carry any R charge. So R charge is conserved. And so the gluon, let's put a square to indicate it's the same. This gluon is the same as this gluon, and this gluon is the same as this gluon. Similarly, this gluon is the same as this gluon. And of course, the other ones as well. This gluon is the same as this gluon. And here as well, this gluon and this gluon are the same because it's just one leg. Something happens, one index of R charge goes here, the other goes here, fine, but then they recombine and R charge is conserved, so this index is the same as this index.
Sorry, gluon or scalar?
Yeah, I meant the scalar. The solid lines are scalar. So this scalar is the same as this scalar is the same as this scalar. If I said gluon, I meant scalar. It was a gluon in 10 dimensions, but now it's a scalar. So you agree that it carries some R charge that is conserved, and therefore it's the same here and here, here and here, here and here, here and here. Also here and here, because it's just one, this line, this index m must go to some index n, but the only thing that can happen is delta mn. Now here it's a little bit subtle because you have, if you think of this as phi a, as two indices a, b, they split. One goes to one fermion, one goes to the other fermion. But okay, fine. Then they recombine and they give the same index, right? The indices are conserved. So similar here. If I have this scalar here, it's going to be the same as the scalar here. So all these diagrams that we draw, except the first one, all these ones, everyone here, plus dot, 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 all these ones, they are proportional to the same delta AB that we had at tree level. Right? Whatever is in the bottom, the word in the top must be the same. Okay? So they are equal to delta AB times something. Let's call it I for incognito. But from the point of view of indices, it's proportional to delta AB. Now we are going to find I by an indirect argument. And the idea is we just need to focus on this diagram. If we do this diagram, then we can get I through a trick. Because we know it's proportional to delta AB. And so this diagram here is all we need. But we did this computation already, right? You remember, we did it. It is just two propagators of phi that go here, two propagators of phi that go there. That was the phi square of x, phi square of y correction that we did already. Right? When we were doing things. Now we only have to decorate by the indices. So we just need to keep track of the indices. So let's do that part. Okay, I can do it here. So the result is the following, plus, and now this diagram here gives you what? It gives you the following. Well, let me write the result. You can tell me what it was, but it was something like this. Well, it was. Okay. Let's first compare this diagram with a tree-level diagram and see that this diagram has two extra propagators compared to just connecting the line straight, and one extra vertex. So in total, it has an extra power of g squared. Do you agree? Because each propagator is g squared and each vertex is 1 over g squared. So two more propagators, one more vertex, so one more power of g squared. And how many more loops you have in n compared to just connecting the line straight? One more loop, right? You had 1, 2, 3. Now you have an extra one here. So one more loop. So 1 g squared and 1 n, so it's a 't Hooft coupling. Right? 't Hooft coupling is g squared times n. So perfect as we wanted, things organize nicely with 't Hooft coupling. And then what we have this loop diagram, and this loop diagram was giving this logarithm of the distance between x minus y squared divided by epsilon squared. And then finally, we have to be careful with the indices. If this index is m, and this index is n, m prime, and if this index is n, and if this index is n prime, there will be here some tensor that we are going to compute in the next blackboard that will be a given number for different m, m prime going to n, n prime. And everyone else, you just connect with delta function. So then we have a delta, let me write like this, a prime, b prime, where this prime stands for the other indices. Okay. And then plus the other diagrams that we said are I, this thing that we don't know, it will also be proportional to the 't Hooft coupling. Let me put a lambda here explicitly, times delta AB. And here, if we do the computation carefully, there should be some total pi's remaining that I don't know by heart, but probably some 1 over pi square, maybe 2 over pi square. This was just from doing that Feynman integral, right? There is some pi's there. Okay, so what is this tensor here? So let's work it out. Now, the scalars, now there are a bunch of options that these scalars can connect. And when they connect, one thing that can happen is that m, so we have this, let's write this vertex, pi m, pi n, which is pi m, pi n minus pi n, pi m square. And so this vertex is equal to the square of this term, pi m, pi n, pi m, pi n, plus the square of this term, but we are computing this inside the trace. So inside the trace, the square of this term and the square of this term is the same, right? Because it's alternating. So just 2. And then we have the cross term, which gives me minus 2 pi m, pi n, pi n, pi m. In other words, I can put the phi m here in the middle because it's in the trace. You agree? And so from the point of view of just following the vector index, you would draw this, you would say it's a diagram like this, where if I follow the trace, if I write this inside a double line notation, I draw the double line, but then inside I say where the index goes, this scalar goes there, and this scalar goes here. This would allow me to keep track of the indices, right? But then I'm erasing the double line and keeping the interesting part now, which is just the SO6 index. So from SO6 we get this. While here we contract the two neighboring guys, and so here we get this vertex, where from the point of view of SO6 it would be the two neighboring lines that reconnect. Correct? Do you agree? And so now here, when we have this index, this here, m, m prime, n, n prime, there are a bunch of possibilities we could write. One option is saying that index m becomes equal to index n, and index m prime becomes equal to n prime. That's one option. The other option is that delta m becomes equal to, say, m prime, and delta n becomes equal to n prime. And the last option is that delta m becomes equal to n prime, and delta m prime becomes equal to n. And now we should work out the relative coefficients between these possibilities. So this one, where they connect like this and like this, which vertex should I use? The first or the second? To get this possibility.
Second.
The second, right? I need to connect this vertex where they connect like this and like this, right? And I can connect the vertex with this being in the bottom or these two being in the bottom. So there are two possibilities. And there is a -2 here. So in total, there is a -4 here. What about this one? M goes with m prime and then goes to n prime. Should I use the first or the second?
Second.
Second as well. And again, I can connect the vertex like this or flip it around, which is the same thing, and connect it like that. So again, -4. And what about this one? Now, the first, right? Because they connect crossway. And any rotation of the vertex gives me the same thing. So there are 4 possibilities. So +8 times that. And so this thing here is that tensor T m prime n prime. Right? This is that combination up there. And so in sum, we conclude that if I have some O, A, O, B, it's going to be equal to some number, lambda to the j, over x minus y to the 2j. And then there is just delta AB, which is delta, let me now write explicitly, m1, n1, delta, mj, nj, the first term. And then there is some minus, okay, or maybe plus, doesn't matter, plus or minus 2 lambda over pi square times some logarithm of x minus y squared divided by epsilon squared. And then this logarithm multiplies a structure where I sum over small j, and then for the most part, I get Kronecker deltas. M1 goes to N1, delta M up to position j minus 1 goes to N j minus 1. Then here, I insert this tensor T, Mj plus 1, Nj plus 1. Sorry, I don't want to close the parentheses yet. Then, let me put here, and then I have delta of the n m j plus 2 go to n j plus 2 delta m capital J goes to n capital J. So this almost everything contracts directly except here. And there was also the contribution from I that we did not know exactly, but it's some term here, some constant, times delta, where they just contract directly. Mj goes to Nj, and Mj plus 1 goes to Nj plus 1. right? Yeah.
How do you know that? And we know that because the one loop calculation is universal, it's going to have the same spatial dependence.
Right, so we know that by dimensions, all these one loop computations, we know we are dealing with a CFT, so we know we are going to generate the same logarithmic dependence. And indeed, you can see that maybe it's not totally obvious, but all of them will generate the same log dependence. So you would have to do some counting to see, is this diagram also giving the same type of logs? Yes, and so on. All of them will give the same type of logs, but what matters is, for this purpose, that they have this index structure like that. So in summary, what we see let me write in a notation that's perhaps more intuitive, that OA, OB is equal to some three-level expression, something doesn't matter, divided by x minus y to the 2j, and then there was this delta AB minus lambda, the log of x minus y squared divided by epsilon squared. But now, instead of a number, like we were getting in our toy example of phi squared, etc., we are getting some big matrix H, AB. Plus, and then, at one loop, it's this. Right? Remember, in the example we did versus the example we did before, which was a toy example, phi square with phi square. It was giving the similar thing, but here it was 1 instead of a delta. And here it was the same thing times a number instead of a matrix, right? And here we add minus lambda log of the same thing times a number. And you remember the conclusion here in this line was that this phi, we could define some O of x that was phi square of x times epsilon to the power lambda times this hashtag, and then this operator at dimension, which was 2 plus lambda hashtag. And this was the quantum correction to the dimension. Right, so this is what we had before, and this is what we have now, right? So how do we go from what we have now, which is more complicated, to what we had before? What should we do? Instead of 1 and the number, we have delta AB and the matrix.
Diagonalizing the matrix?
We diagonalize the matrix, right? So if you diagonalize the matrix, we go from the first line to the second line. So it's clear what we should do. We should first find the operators O that are defined as some linear combinations. Let's use psi A OA, some linear combinations of these operators OA, where these psi A are chosen such that they diagonalize this matrix HAB. Right? So we take linear combinations such that when I plug these linear combinations, I diagonalize this HAB. Right? Then, with this operator, this equation here becomes that the expectation of O. Now, maybe let's write like this. These operators O, there are a bunch of them, right? You diagonalize a matrix, you have many. So let's put here On. So that On with OM will be equal. Well, N needs to be equal to M, delta Mn divided by X minus Y to the 2J. And then we get 1 minus lambda times the eigenvalue, the nth eigenvalue, times log of X minus Y squared divided by epsilon squared. Because we diagonalized. Right? And now we just define our O renormalized and to be just epsilon to the lambda gamma n times On. Right? And then this operator On renormalized with OM renormalized. Now it's what we expect in a CFT, delta Mn divided by X minus Y to the dimension n, where delta n is just the same delta classical, that was J for everyone, plus the anomalous dimension n. And so what we need to do is diagonalize this matrix, and then the eigenvectors of the matrix tell you what are the good linear combinations, what are the good primaries that have definite dimensions. So the eigenvectors give you the operators, and the eigenvalues give you the dimensions. Right? Now, notice that now there is a convenient way of thinking about this operator. We can think of this H, we can think of it as a quantum spin chain Hamiltonian. So let's explain this. How do we do this? We just think of our operator, OA. I think of it as a spin chain where in the first side I have a degree of freedom M1, in the second M2, in the last one MJ. So it's an SO6 spin chain where this value takes value 1 to 6 and so on. So this is an operator. This is a cat that lives in the product of V tensor V, where each of these V's is just some 6-dimensional object. This will be the Hilbert space. You agree that OA is equivalent to this, just notation. This is the same as trace phi M1 phi MJ, right? They have an order, so I can just write it like this. Just saying that I have position 1, position 2, position 3, etc. And I just keep track like a cat like this. And then my H acts on this vector with index A and gives me a vector with index B. So it acts on this spin chain. And then how does this H act? Then my Hamiltonian of my spin chain, H, the object that I need to diagonalize, you see that it does nothing except locally at positions n and n plus 1. So this H is a local Hamiltonian. It's a sum from n equal to n up to the size of the spin chain. And then it just acts with an Hamiltonian density at positions n and n plus 1. Otherwise, it does nothing. This locality came from planarity. And then what does this Hamiltonian do, this Hamiltonian density? It acts on two neighboring spins, m and n. Right? Maybe we can put a lambda outside here explicitly, a 't Hooft coupling, so that we don't worry about it. Maybe some lambda over some pi square. We don't care about the pi square. And then what does this Hamiltonian do to the spins? Well, it can permute the spins. It can swap these two spins. So it can give n and m. That swapping of the indices comes with coefficient 8. So let me normalize and say coefficient 2. I normalize by, I put the 4 here. There was a 2 pi square. There's a 2. So this would be what we would say. It's 2 times the action of an operator that permutes the two sides. This is what's called the permutation operator. Then it can annihilate this and produce any number of them, or it can, this one here, or it can do nothing. M goes to n and m prime goes to n prime. So there is another term which is plus. This one is something that I'm not sure, times m and n. This would be something times the identity operator acting on mn. This I don't know because it comes also from this incognita term that we did not compute. Right? The identity part is the part that receives contributions from the incognita. This I don't know for sure. This I don't know. And then the last term is plus. It could produce any E and P if m is equal to n. Right? This would be this possibility of n equal to n prime. It's this term here. That compared to this one that gives 2 would come with a coefficient -1. And this would be the definition of the so-called trace operator acting on m and n. So these two operators are the usual operators you would write in an SU2 spin chain, that all you could do is swap the spins, is hop the spins and do nothing. And this is something new that you would do in spin chains that have SON symmetry. You can annihilate the spins and create any pair of spins. And so we conclude that this is our spin chain where this Hamiltonian density is then twice the permutation operator on sides n and n plus 1 minus the trace operator on sides n and n plus 1 plus some number times the identity operator acting on sides n and n plus 1. And so we conclude that we have a local Hamiltonian and nearest neighbor Hamiltonian. And if you diagonalize this local Hamiltonian, you get the eigenvectors and the eigenvalues. And in particular, you get the spectrum at one loop of n equals 4 super Young Mills in this scalar subsector. Is it clear? Now, of course, so now we want to ask, what's this constant? So we finish our game. Right? And that's it. And then we want to say, what can we do with this problem? How can we make progress in this complicated problem? Now, how could we go about computing this constant? Any suggestion? What is this constant? This constant is equal to -1 plus whatever the other diagrams give, right? But that's not very convenient because we don't know what the other diagrams give. So how could we try to fix this constant by another argument? So first notice that this constant is just an overall shift of all the energies because it's proportional to the identity, right? So we solved the most interesting part of the dynamics is done. Right now we just have some Hamiltonian that there is some overall ground state energy that we don't know exactly where it is. So how could we go about fixing this overall shift?
We fix it to 0 to make ground state become 0.
To make what?
The energy of ground state becomes 0.
But why would we do that?
We like this.
Why?
Most of the time it's good to have 0 energy ground state.
Sometimes it is, yeah. Sometimes you should.
Could you use the fact that like f squared receives no quantum corrections to try and cancel?
F squared doesn't is not an operator made out of scalars, right?
Oh, right, yeah. Or the
Z to the J.
yeah.
Good idea, right? So now we can use the fact that Z to the J should get no quantum corrections. Right? But trace of Z to the J should or must have gamma equal to 0. So let's see how it works. So this operator here, right? It is just Z, Z, Z. Trace, right? And you can ask now, what happens when we act with Hamiltonian density on this pair of Z and Z? Right? Locally. Well, if I go to that language where we know how to act, this object, like we said before, it's 1, 1, minus 2, 2, plus I 1, 2, plus I 2, 1. Right? So now let's just act on this operator. So first of all, the trace. What does the trace do acting on this operator? What does it give? 0. We said they are symmetric traceless, right? That's why we argued this was the same representation as this. Indeed, it gives 0. We see explicitly because here 1 is not equal to 2. And when it acts here, it gives the same as when it acts here. So it just cancels. What does the permutation give when you act here compared to what the identity gives when you act here? The same, right? Both the identity and the permutation give back the same state because this state is symmetric. Right? And so the Hamiltonian acting on this state just gives me 2 minus that number that we don't know times ZZ. So this number is equal to 2. And so we conclude that the dimensions of these operators, trace, phi I1, phi ij, are equal to the energies of a J-site spin chain with a local Hamiltonian H, which is just some overall normalization, some lambda, this I'm not sure. And then that would have to do the diagram carefully, sum from n equal 1 up to j, and then the local Hamiltonian density twice the permutation operator acting on sides n plus 1 minus the trace acting on sides n and n plus 1 minus twice the identity operator acting on sides n and n plus 1. Now, this is still not trivial. It doesn't mean we solved completely the problem. Solving this spin chain is still hard because we have, of course, a 6 to the j times 6 to the j matrix typically, right? It's still an exponentially hard problem. If you have 6 scalars, you have a huge Hilbert space, right? You have 6 options at each side. It's a complicated problem to solve still. Now, some problems in 1 dimensions of quantum spin chains are better than others. Some problems are exactly solvable. And some spin chains are integrable. Some spin chains can be exactly solvable. And so now you can go to a book and ask which spin chains with SON symmetry are integrable or with SO6 integrable are integrable. And what you find is that if this coefficient is minus twice this one, so if the ratio, this ratio, which is equal to minus 2, is precisely what says that this spin chain is solvable. And this is the beginning of a big story that we are not going to go over. This was a discovery by Minahan and Zarembo in 2003 that they did this computation and they found exactly this number 2 and minus 1. And they said this is exactly the combination that allows us, of all possible ratios, this is the one that allows us to solve this model. And therefore, they could compute exactly in a very simple form all these eigenvalues of the spin chain.
Sorry, is that an if and only if? Being minus 2?
Yeah, it's integrable only if the ratio is minus, maybe if the ratio is 0, it's also integrable, if there's no permutation. That's another type of Lieb spin chain. But if they are both non-zero, the ratio needs to be minus 2 for the model to be integrable. And why is the ratio minus 2? Because it's not any random theory, it's this theory with this precise commutator square. And why was this precise commutator square? Because it came from 10 dimensions. And it was just a trivial f squared in 10 dimensions. And why was it in 10 dimensions? Because it came from string theory. Right? So it's a gift from string theory. Really, the disintegrability is really a sign of, is really a sign of that this theory was a theory coming from a higher dimensional theory that was string theory. And so what we see here appearing is this big field of integrability. I think you are having some courses on integrability, right? With Kevin? No? Not this year? But integrability is a big subject in physics that some models in 1 dimensions can be exactly solvable, like these quantum spin chains. And what this leads to is to knowing the spectrum analytically, and not only at one loop, but this problem of computing the spectrum for any coupling lambda is solved. Okay. Of course, this is a big arrow. It will take a full course just to explain. We just did one loop for a subset of operators. But let me just say a few words about the full problem. So first of all, there are 2 things I could, 1 more minute please. Just 2 things we could say. One is how to go to all operators, not just scalars, but we could generalize to all operators. And we could also generalize to all loops instead of just one loop. Right? And of course, that's both are interesting and both are non-trivial. And then there is the question of how do we solve this? How to solve it, and that's where integrability would kick in. So just to finish, and because we have the material here in these blackboards, let me just tell you, because there's a beautiful spin chain that describes all operators at 1 in n equals 4 super Young mills. We found this SO6 spin chain, and now I could tell you what is the general spin chain for any type of operator. And so here it is. So the idea is the following. Now we have a spin chain that now our spin chain states psi. Instead of having an integer m1 up to mj, now we have a letter chi1 up to chi_j at each site where chi is one of those operators. Right? So it's already, you see, it's a non-compact spin chain now. Right? In particular, because we can put any number of covariant derivatives. So it's an infinite dimension. So a way of thinking, okay, now, so this is the first thing. Now the Hamiltonian will be, by planarity, a sum of Hamiltonian densities acting on sites n and n plus 1. Okay, so that's just by planarity. Then this Hamiltonian density, let's put double line, acts on the words chi and chi prime and gives some number c times chi prime prime and chi prime prime prime. Right? Do you agree? Now the rule is the following. Suppose here, in these operators, you have some oscillators. Right? You write them with oscillators. Right? And here, you have other oscillators. And then what you do is you move to write these new fields. They have different oscillator content. And so what you do is you move n 1, 2 oscillators from this side to this side. And you move n to 1 oscillators from this guy to this guy. That's a way of getting these operators chi prime prime and chi prime prime prime. Now, which ones do you move? Do you move A daggers, B daggers, C daggers, or what? It doesn't matter. You just tell me that you move n12 from here to here and n21 from here to here. That's all I need to know. Then this coefficient depends on n, n12, and n21, where n is the total number of oscillators. Again, just to be concrete, if these are scalars, there are 4 oscillators in total. N would be 4 in this case, if it acts on 2 scalars. And then when it acts on 2 scalars, I get 2 scalars again, but I can reshuffle the oscillators, and therefore this n12 and n21 could be whatever they want to be. And you sum over this n12 and n21 that reshuffle these operators. Right? And it turns out that the full quantum spin chain can be just summarized, can be just given if I now give you what these C's are. And so this is that you just need to know the total number of oscillators. How many oscillators? So this is the total. This is the number that go from chi to chi prime. You take some from chi and you put it in the other slot. And then you have n21. This is the number that you take from chi prime and you put it in the chi slot. Right? So you take some from here and you put here, some from here and you put there. And this result that encodes any possible state is just equal to the -1, that is, okay, a boring -1, I'm not going to write here in detail, times the beta function of n1, 2 plus n2, 1 over 2, and then 2 plus n minus n1, 2 minus n2, 1 over 2. If n1, 2 and n2, 1 are not equal to 0, and it's equal to the harmonic number of n over 2 if n1 plus and n2 are both 0, where this harmonic number is just the sum 1 over k up to n. And this beta function is just a bunch of gamma functions, right, that you probably saw in string theory. And this is the full spin chain that now describes any operators acting. This is called the harmonic action. And this spin chain, of course, I already told you, is also an integrable spin chain. And so the full one loop problem can be solved. So it looks non-trivial, but if you restrict to just scalars, this fun expression becomes what we just described there for the scalar. If all you have is 4 oscillators, and you can just move these 4 oscillators around, and you work out the weights, you would get this 8 minus 4 minus 4 that we got before from just summing over these possibilities of reshuffling the ends. Okay, so I think this is a good point to stop. Sorry for going over time, and let's continue tomorrow. We said, let's start exploring the dynamics of n equals 4 super Young Mills. We saw it's a conformal theory the day before. So let's start exploring the dynamics of this CFT. If we care about the CFT, we care about the CFT data, which is the dimensions and the 3-point functions. So we started by the simplest observable in this gauge theory, which was getting half of the CFT data, which are the dimensions, right? And this is what we found. We found that the dimensions of physical operators are nothing but the eigenenergies of quantum spin chains. It's interesting because the quantum spin chain is something we are very used in condensed matter, and here we are studying some high energy gauge theory, but it's the result. So the energies, the dimensions of these operators are the eigenenergies of a quantum spin chain Hamiltonian. The map from operators to spin chain was trivial. It is just the fact that we have a trace, so there is an order of fields. And all we did is we map phi1 to degree of freedom m1, etc., phi mj to degree of freedom mj. So I have a spin chain where at each side I have 6 options, so it's an SO6 spin chain. And this is a local spin chain where the Hamiltonian we have to compute, it interacts with spins at position n and n plus 1. I can represent its Hamiltonian density like this to indicate it takes 2 neighboring sites and that's it. And it's local and it interacts on 2 sides just because of planarity. That will be true in any large n theory. It's not special to n equals 4 or anything, right? It's just that as soon as you have planarity, you are going to draw local interactions because the interactions cannot jump because that will be non-planar. And so planarity, just large n, tells you that this Hamiltonian has to be local. So that was a given. And then we asked, so how precisely can the fields get shuffled? And they can get shuffled when we do 2-point functions by studying interactions. And we saw that the most interesting term was this one where the scalars are shuffled, where it acts on the spin chain and gives a different state. And the spins can either be permuted or annihilated and created again. That's the permutation and the trace. And this precise coefficient, a 2 and a minus 1, came from just this particular interaction. The fact that the interaction vertex is this commutator square. This vertex, on the other hand, came from string theory. It was because it was a low energy limit of a 10-dimensional theory that we have this very particular interaction. And it turns out that the fact that these coefficients are precisely tuned like this, that of all possible SO6 spin chains, we got the solvable one. So we got exactly the one that is exactly solvable. And it's a long story, this wiggly line, that I'm not going to tell you about in these lectures. But there is a big subject here. And in particular, after we studied this one loop, for these scalar operators, people generalized in many directions. And now the problem of computing the dimensions, which is half of the CFT spectrum, is solved. So this problem is solved. Now, to generalize it, there are many directions we have to generalize what we did in the lecture. One is, in the lecture, we did scalars. So we should do all the fields, not just scalars. Now, if we do all the fields, instead of having a degree of freedom from 1 to 6 at each side, we have a letter at each side, which is made out of these oscillators, A, B, and C. Right? And so you act on these two letters, one letter here, and you get two other letters, which are reshuffled. And so the way the Hamiltonian works is very simple. You just take these oscillators, you take this, and you take some from here and you put here, and you take some from here and you put there. How many do you take from here? N1, 2, and you put there. How many do you take from here? N2, 1, and you put here. And then the answer is that the action of the Hamiltonian is just a summation over how many you take from here to here, doesn't matter of what type it is, and how many you take from here to here, and you sum over those two numbers, times a constant that only depends on the total number of oscillators, on how many jump one direction, how many jump another direction. And then we get the cat after this reshuffling. And this constant was very simple. I wrote it yesterday. It was a bunch of some simple beta functions. Now notice that it's not like you can put any combination of oscillators. In fact, if you look at your notes, at our list of words, you can easily see that the number of A's minus the number of B's plus the number of seats at each site is fixed. Right? You can easily look. If you look at what we wrote, you can easily, so it's fixed to what? Tell me, what number should I put here? If you believe me that it's fixed, you can just take your favorite letter and just tell me what this number should be. What would be the simplest letter with the smallest number of oscillators? Or you can look at the list. Two, right? It's true. You can check the list that it's true. But you can also but once I tell you that it's constant, the scalar has two oscillators, right? C dagger C, for example. Or F has two oscillators, A dagger, A dagger. So once you know it's fixed, it's obvious that it's 2. So you start with some word that has many A's, many B's, many C's with this condition. Another letter here that has many A's, many B's, many C's with this condition. And you move them around. And that's it, and you get this harmonic action. So in the tutorial, you are going to play with this harmonic action, taking this harmonic action, and seeing what kind of spin chain Hamiltonian we get when we restrict not to a subsector of scalars, but to a subsector which is more related to gluons, a different subsector of the theory. And the reason for studying that subsector, I will explain tomorrow. Now, so we got a local Hamiltonian at one loop, and then there are higher loops as well. So one direction is going to all operators, that is this. But the other is not staying at one loop, but going to all loops. Okay? Now, at all loops, what would happen? So what would happen at 2 loops? Right? If we repeat the kind of exercise we did in the lecture now at 2 loops. What would happen to the Hamiltonian? It's still planar, so it's still local. But it's 2 loops. It's not just one loop. Right? So what could happen to this local Hamiltonian?
Operator instead of one operator, like PP.
Exactly. So now it doesn't need to be nearest neighbors. It could be next to nearest neighbor. And so these corrections, so what we write is that we have lambda times the local Hamiltonian plus lambda square, and the Hamiltonian now would be next to nearest neighbors. It could involve 3 local spins giving 3 local spins, and so on. So it's an Hamiltonian whose range is increasing in perturbation theory. And so we get some long range Hamiltonian. Of course, it's long range, but there's still a hierarchy, right? If lambda is small, maybe nearest neighbor, next to nearest neighbor, and next to nearest neighbor I keep, but the other ones I can drop. So there is a range that decays, right? Because it's more and more suppressed with lambda, but the range kind of increases. So we start with a local spin chain, and then it's a little bit less local, a little bit less local, a little bit less local. And as the coupling increases, so this becomes less, let me write like this, ultra local, right? Because we start, it's really ultra local. It's not like there is some decay, right? We start and it's just ultra local. Only the neighbors interact. Then only next to neighbors interact, right? So it's zero interaction after that. Right? That's what I call ultra local. Local, I would say it's something like decays very fast. Right? So we go from being less ultra local as lambda increases. To the point that eventually, when lambda is increasing, well, to call it a local Hamiltonian no longer makes much sense, right? So then, eventually, we can say that if we think of this object really at finite lambda, I can say it's the Hamiltonian of some 1D system. Maybe I shouldn't call it spin chain if lambda is finite, right? Because it starts to interact still kind of local, but not so ultra local. And so we could imagine that this 1D system, I can think of it as some string. Right? It's just my 1D object, the trace, right? We saw that this trace that we could consider. You could think of it as like a closed loop of string. And so the proposal would be that these energies, if this is correct, if you can think indeed as these very dense diagrams, as some kinds of energies of some strings, this should be given by the energies of some string theory. And today, we will see what that some string theory is. So let's leave this space here to see what could this string theory be. But anyway, with integrability, with these exactly solvable techniques, people can order by order and eventually even resum everything. And so this problem is solved. The dimensions are known. So you can plot dimensions as function of coupling. Right? What kind of things do you get? For example, there is one plot that we know is this boring one. It's just an horizontal line. That's if the operator is protected. The operator is protected, the dimension is the classical dimension, and it doesn't matter what coupling you are, you just draw a straight line. But most operators are not protected. Most operators are the non-zero energies of the quantum spin chain. Right? Those start classical plus one loop. So one loop gives you the slope. So this slope here, the beginning of the curve, is what are the eigenvalues of that Hamiltonian. And then there is lambda square correction that bends this curve a little bit, lambda cube, lambda 4, etc. There are all the quantum corrections. And if you were to solve it, this is what you would get. You would get that the energies grow and they diverge as lambda goes to infinity, typically with lambda to the 1/4 power. And so this would be a theory where if this is a string theory, there are some strings that have some fixed energy and all other strings have very big energy. This is to be a string theory. Okay? Good. So that's a summary of what we have seen so far. Now, so today, the goal of today's lecture is to tell you, is to try to guess what is this string theory. And by telling you what is string theory, I will have an equality between a gauge theory and a string theory, and that will be AdS CFT. That's the duality we are after. Okay, so today we discuss the decoupling argument. Okay. So our basic idea is we want to think of this system in two different ways, either as a string theory or as a gauge theory. So let's think of another situation where we could think of our quantum system in two different ways. Suppose we consider a proton. This would be a heavy proton. And then here is an electron. So a light electron. Now, what happens to the electron in the presence of the proton? How does the electron interact with the proton? They exchange photons, right? So there is a photon being exchanged between the proton and the electron. But that's just one option. There are other things that can happen. They can exchange the photon, and we can emit some photon here. Or they can emit after they interact. This effect, for example, this effect of this emission is what's called the Bremsstrahlung, something like that. I think there is one more letter here. There are two S's here, I'm not sure. And then A as well. Strahlung, yeah, Bremsstrahlung. Very good. This Bremsstrahlung effect. There are other things that can happen, right? We can have the proton and can interact with the electron, and there can be something like this. This would be a vertex correction. We can have some vacuum polarization effect. Right? This would be some vacuum polarization effect, etc. Plus ... And at the end of the day, this could tell us questions like, if I have my proton and my electron that's going to be deflected, it will tell us some things about these angles, etc. We would learn how the electron is deflected and so on. In particular, we could compute the potential between this electron and the proton by summing these diagrams. And the potential between this electron and this proton would be something like there will be the Coulomb force, alpha over r. And then you were to start computing these quantum corrections, in particular due to loops of the electrons and so on, and you would get something like 1 plus alpha over 4 square root of pi e to the minus 2 mass of the electron times r, some exponential decay like we saw in the first lecture, times mass of the electron times the radius to some 3/2 power plus ... And so here, to think of the electron, let me point out that there are two things we could do. One is, suppose we could compute this potential, the effect of the proton exactly. Right? And the other option would be, there's no potential, there's just a proton that interacts with the electron, and we sum over all these possible Feynman diagrams. And so we have 2 points of view. We can either think that we have the sum of all these diagrams, where we have this, where the electron interacts. Or we can say that this is the same as the electron moving in a non-trivial background. By this blob, I mean some non-trivial background. That here, I would say, is encoded in this potential where the electron moves, this Coulomb potential. So it feels that there is something there. And I remove the proton and I replace the proton by a non-trivial background. And so this I would call the field theory picture. And here, this electron, this would be the analog of some kind of gravity picture. Of course, there's no gravity in this picture, but you understand what I mean, that there is some background that the electron moves differently because the background is not just empty. And this would give us a flavor that there is these two pictures that we can think. We have A, that would be the analog of n equals 4 super Young Mills, where we have some field theory and we sum over all possible interactions. We start at one loop, two loops, etc. That's the kind of things we were doing there. And we could ask whether there is a new description, B, and the equality between the two would be this duality we are after. So that's one kind of idea we could pursue. Now, for us, here, instead of a proton, we'll consider another heavy object, right? Here what's important is that the proton is heavy, right? And instead of a proton, let's consider a stack of d branes. Why not? So instead of the proton, the idea is to consider a stack of n d3 branes. And instead of the electron, let's think as some flying closed string, for example, that is passing by this stack. And so we would have this picture where we have the stack of d branes here. There are n d branes. And then there is a closed string that is coming here and approaching this stack of d branes. And then it will go out here and get out of this stack of d branes. Now what does it do, this string? It approaches. Eventually this point could touch here. Now it can open up. It can reconnect. Now it's flying on the d brane. It's an open string now. And it can propagate on the d brane. And it could then do these kind of things that we saw. The string could split into two strings that can propagate. Then they can reconnect again and move like this. And eventually the endpoints are close, and then they are very close, and then they fly apart. Okay, where this would be, here I'm representing time, a movie of the particle going here. Or equivalently, if I try to draw it in a more two-dimensional notation, I could have something like this. I have my closed string. It interacts with my d brane, and then it gets out. This is one possible diagram. Plus, another possibility is the string comes. It we draw something more similar to this. It interacts here, and it goes out. But here, if I can draw it, it's something like what I drew the other day. You see, so there is this. Right? You see that this is the same as that, right? There could be other things, like the string could do this, interact once, interact another time, and then leave. In the process, the string could have holes here, right? It could have some genus, it could open and split, etc. And we would have all these possible interactions with the D-brain. Like here in the electron, we have all possible interactions with the proton. And so the question is, can I then sum this all up and replace this instead by the string that moves in a non-trivial background? This closed string that just moves in some non-trivial background. Perhaps still splitting sometimes and joining, but moving in some non-trivial background. And so thinking in this point of view here of the interaction with the D-brain, this would be the point of view A that we know is governed by n equals 4 Superior Mills, and we'll be a little bit more precise in a second. But we know that the dynamics of this stack of brains, right? All these open strings interacting there, that's what n equals 4 Superior Mill takes care of. And here, we would replace it by B, which is some effective closed string theory that we are after. This point B. Right? So more precisely, so in A, from the point of view A, where we think in this direction, we think of more in this direction, right? Then we think that we have open strings. These open strings that are propagating in time. Right? They draw, when they move, they draw our favorite fat diagrams. And this will be described by what? Well, if it's a bunch of strings here, it will be described by Yang-Mills theory plus some massive open strings. It's not just gluons, but there could be also massive open strings. And because we insert something on the brain and remove something from the brain, we would have plus some sources. Right? To inject, to touch the brain and remove the brain. Now, in B, however, from the point of view B, we want to think in this direction, where instead we interpret these interactions with the D-brain like this as a closed string, right? That is being emitted. So that same picture up there I could think as a closed string that is emitted here, drawing this closed string, or as an open string that is propagating from left to right. So this would be the point of view B of sending this closed string, and here this would be the point of view A. And this would be thinking more from the point of view B. B propagates like this, and A, we think of it in the other direction.
In the B case, there are no strings. The B scenario is some background, some non-trivial background, and then there is just the closed string.
At the very end, yes, but we want to understand how that background is generated. So if you think the D-brane, you can think in two ways. It's the object that supports open strings, or it's the object that emits closed strings. Right? So there was here, you have a closed string in red. It came from where? From the D-brane. So the D-brane sources closed strings, or it allows for propagation of open strings. The fact that you can think from one or the other is this open closed duality that I described in one of the lectures. Now, this, of course, thinking of this as a closed string insertion is like thinking that I have my worldsheet and I insert some vertex operator here. I'm putting some kind of closed string. And we are not interacting once with this D-brane. We are summing over, imagining that we have many of these interactions. Let me put a circle indicating that what a vertex operator does is it creates some state that if I cut that state open, then that's the closed string. So I could sum over a bunch of vertex operators like this. That would have a net effect, if I sum over a gas of such vertex operators, of giving me something like some exponential of the integral of some vertex operator over the worldsheet. So this picture here, this would be, what I'm imagining, is some kind of condensate of gravitons. Closed strings, in particular at low energy, are gravitons, like we saw. And so this would be like saying, put many, many gravitons, they kind of condensate, and they create this gas of many, many vertices that exponentiate and effectively shift my action. So this, it's in the exponent, so it effectively shifts the action. In other words, it changes the action of the string, so it gives me a new background. And this would then be the picture B, where now I have my string, and instead of considering all the brane, I think that all these interactions with the brane should be possible to resum, and now I have some closed string in a non-trivial background. Okay, and so the obvious questions that we have here is, there are two obvious questions, one here and one here. One here is, what is the analog of this background, V of r, schematically V of r, of course, what is this background precisely? And here, what is the effective field theory that describes this D-brane? So this question we know already, and I'm just going to remind you that it's n equals 4 super Young-Mills, and the purpose of today is to figure out what would be this potential. Okay. At this is the point where we would answer this question that Anna asked at some point. Why do we put many D-branes? It's precisely because we want to have the chance of having this picture, where we can either think of them as changing the background, and for that we need them to be very heavy, or we want to think of them as being the endpoints of open strings where we have this gauge theory description. Okay. So let's continue here. I forgot, the cutoff today is sharp, or there's some flexibility? There is a lecture at... Okay. Okay, so now the idea is, so let's think of A first, a little bit more. Just to remind you that what do we have? What is the action describing the picture for that stack of brains? There is some action for the bulk, which is just gravity. There is the action for the brain, that is n equals 4 super young meals, and there would be some action for some interactions between the brain and the bulk. Okay. So this bulk action is just would be just gravity plus massive modes, massive closed strings, and so it would be something like 1 over g Newton, that we can write in some convenient way like this, Newton, integral of square root of gr, which would be equal to some integral of theta square after I rescale plus some kappa hdh plus etc. And just to remind you that this stuff here is going to be irrelevant at low energy, just because this kappa is dimensionful, and gravity will decouple. That's what we already saw once. Similarly, this action for the brain is n equals 4 super young meals. Here we also have plus higher derivative corrections that are also irrelevant at low energies. These higher derivatives, these higher curvatures just come from integrating out massive modes. So then you get not only Ricci, but Ricci square, Ricci cube, all these powers of Ricci that have more and more derivatives in effective field theory that we don't care at low energy. Similarly, here we get n equals 4 super young meals plus, but again, if you do it precisely, it's not just n equals 4 super young meals. You would get some effective theory that would contain some f to the 4 plus, etc. You get some other terms, not just f squared and so on. Again, that would come from integrating out all the massive modes. All this stuff here is also irrelevant at low energy. And the coupling is also irrelevant at low energy because gravity couples to our low energy systems. The coupling of gravity is not important. And so what we conclude is that if we take our system A and consider low energy, this is going to be key, we consider low energy, we see that the system A, again I'm being very fast because we already did this once, is equal to n equals 4 super young meals in 4 dimensions plus decoupled 10 the supergravity. Yeah, that's it.
Pedro?
Yeah.
The renormalization comes from the fact that delta diverges, so the correlation function of lots of the fields are going to be 0, right? I have delta equal to j from that diagram. I can see it in IR, otherwise is delta going to be diverged, right? From that diagram.
No, you mean, so this here, this f to the 4, this has dimension 8, right? So it's irrelevant. Right? Even at weak coupling, I mean, it's immediately irrelevant.
If we think about that diagram, if lambda increases, it means we are going to IR, right? Lots of fields have divergent.
Wait. Why lambda increasing is going to IR?
It's not equivalent.
Lambda is Here, lambda is a coupling. There is no beta function. It's up to you. It's a marginal coupling. You can choose whatever you want.
But when we want to go in IR, we need to integrate out lots of diagram, right? It was just my intuition that if I consider lots of terms, like, I don't know. Yeah, it's maybe wrong.
Yeah, here we are always in a CFT. The 2-point function is always 1 over distance to the power delta. It's just that delta depends on what coupling you have. If you turn off the coupling, you get this delta. If you turn on the coupling, you get this one. But I wouldn't say that one is more IR than the other. Now, this description is easiest for small coupling. Right? If the coupling is very small, gauge theory is perturbative, and we solved stuff, right? That's when this description is it. Okay. Now let's switch to B. So A, yeah.
What exactly is supergravity definition?
Supergravity is just a 10-dimensional gravity. The 10-dimensional gravity, that is the strings that are flying far away from the D branes in 10 dimensions. But it's super because when there are gravitons and the partners of the gravitons under supersymmetry, so there are a bunch of massless modes that are flying around in 10 dimensions.
So it's just the 10-dimensional case that we were talking about.
That's right. The same 10-dimensional. No, the 10-dimensional, the closed strings. We were talking about the open strings, right? We started with 10-dimensional. That was super Yang-Mills. The analog for gravity is supergravity that I did not write down, but it's Ricci plus its supersymmetric completion. Okay? But it's decoupled. That's what's important. Now, we think about B, about the point of view B. And so you want to ask, what background does a stack of D branes generate? If you put a stack of D branes, what background does it generate? And so you put a stack of D branes. And you want to ask, what's the low energy limit from the closed string point of view? So now you ask, what background does it generate? And you solve Einstein equation with a source that is a plane. So you are going to write the low energy effective action. And you are going to solve the Einstein equations that follow from string theory. And you get that the metric for a stack of branes is equal. Again, let me just write. This is found. You find this by solving the general relativity equations that themselves follow from the string effective action. That itself follows from either matching closed string amplitudes or imposing that the beta function of the two-dimensional string is equal to 0. So when you have a string theory that's moving in a two-dimensional background, it cannot move in any background. One background is flat space. But you can try to put on another background. So you write a sigma model where you couple the string to any background, right? And then that sigma model, that background is like couplings for the string, right? It tells you how the various fields are coupled to, right? Instead of just dx dx, you have dx dx with some couplings behind, which are the background. Now, those couplings would in principle have a beta function. And if you impose that the theory is a CFT and the beta function is 0, you show that these backgrounds obey Einstein equations. Right? So that's how string theory predicts Einstein equations. Equivalently, you can say, I don't want to do that fancy stuff. I just want to write what action reproduces the scattering of gravitons, for example. So what do? I study in string theory the scattering, which is just some correlation function of vertex operators. I compute it. I take the low energy limit, I get some numbers, and I write down an action that matches those numbers. And I compute many, many amplitudes, and I write more and more terms in my action, and then I resum, and I get some effective action. Then that effective action is just Einstein plus some other terms. And when you compute the Einstein equations, you can solve and now get the background. Okay? Again, this is stuff that you are taking string theory. There's no string theory course. There is kind of a string theory course. Anyway, if you were to study chapter 1 of Green-Schwarz-Witten or Polchinski, that's a standard thing that this beta function equals 0 or matching of closed string amplitudes is the standard way of deriving Einstein from string theory. And so we compute this metric, then you solve. It's a simple problem where you have some orthogonal directions xm and some directions here x mu, and you have to solve putting some delta function source for a bunch of d branes here. So it's like solving for a Schwarzschild metric, but instead of having a point, you have a plane and so on. So you solve it, it's not complicated, and you get the following. You get eta mu nu, dx mu dx nu. That's nice. Dx mu dx nu. So that's nice. There is translation invariant in this plane. That makes sense. There is also a term which is dxm dxm. That makes sense. There is rotation in this 6-dimensional plane, right? So this mu runs from 0 to 3. This m runs from 1 to 6. And then the fact that you are solving for this background, there is some term here that is square root of 1 plus L to the 4 divided by R to the 4 plus, and here there is square root of 1 plus L to the 4 over R to the 4. That's the analog of this blackening factor in Schwarzschild, 1 minus 2 pi m over R, where R is the distance from the d branes, so it's square root of xm xm, and L is related to the charge, to how many d branes there are. So L to the 4 is equal to G string times n times 4 pi alpha prime. If you put many, many d branes, right? Yeah, it's like having a big mass, a big charge. If you put 0 d branes, then you drop this term and you get flat space. Right? If you turn off, so you need n to be big. If you send this G string, you can think of it as G Yang-Mills squared, the G that appeared in n equals 4. And this thing here would be the Tooth coupling. And if you want this coupling of string to go to 0, you want to take this n to infinity with this Tooth coupling fixed. If you want to have it to be in the regime of perturbative string theory, then you want to take this Tooth limit that we said. Otherwise, this L would go to 0 and it would go back to flat space. In other words, if you don't put many branes, they are probes. They don't change the geometry. But if you put many, they start back reacting and the geometry gets deformed in this way. Now you see here that this description, we can already anticipate that whatever is going to come out here, this is going to be easy to deal with for lambda much bigger than 1, which would mean that L is large. And we have some small curvature. We have some things change over R big. Therefore, gravity is optimal when this L is large. Right? You want things to take a long time to change.
why is it easy for lambda much greater than 1? We were keeping lambda fixed and taking different limits to
this L being large means that the effective size of the geometry, which is L, right? It's by when you start seeing modifications of the geometry, is big. And so that means that this L is big, but it's big in what units? Alpha prime squared is the string length square, right? So this is saying that this length is big in units of string. Like you have some small string, some fundamental scale, and this length is much bigger than the typical length of a string. In other words, the curvatures are big, and therefore the string has some effective description. If the curvature was very small, the background would change at very small scale. It would be a very stringy background, where you would start putting the curvatures very small, and you could excite small strings, right? So the curvatures, the length scales become very large, therefore as large. So L is many string lengths. Right? Okay, so we have this background that we are now going to analyze. So let's look at this background. And say, let's study this background at R much bigger than L, which means far from the brains. And then let's study this at R much smaller than L, which means close to the brains. So first, if R is much bigger than L, what do we get? What happens to the metric? If R goes to infinity. Right, that makes sense. There are the brains, you go very far away, you see flat space. So if we go very far from the brain, we get flat 10-dimensional space-time. Right? And so here, very far away from the brains, we have, if we think of low energy, we have 10-dimensional supergravity. Again, we are always thinking about low energy. So at low energy, far away from the brains, there is gravity going around. Right? Now comes the fun part. Let's now go close to the D brains. So if R is much smaller than L, what happens to this metric? It becomes the following. Then ds square. Now it's the opposite. In the square root, instead of keeping the 1, I keep the other term. Right? That's the one I like. Now it's not 1, but it's the other term. And we get R square over L square eta mu nu dx mu dx nu plus, and then there will be L square over R square from the second square root. And now let's go and write that in radial coordinates. So we get dr square from the 6 dimensions, right? Plus r squared times the sphere. So the r square cancels the r square, so we get plus L square times the geometry of a 5 sphere. Right? So this was just a clever way of writing the 60 part of the action. I just split radial part and angular part, right? Is it okay? It's dr squared plus r squared, the sphere. Now here, we see that this space, this is a sphere. It's an S5. And what is this space here? Well, this space here, you might not recognize yet, but if you write R equal to L over Z, then this becomes eta mu nu dx mu dx nu plus dz square divided by z square. Maybe there is some L square here, but that you can just absorb by rescaling x. And what's this metric? AdS. And so this part is just AdS 5. And so we find this background AdS 5 times S5. Right? So close to the D branes, we see this AdS 5 times S5. Now we want to ask what happens at low energy. Right? But now we have to be very careful. Because what do we mean at low energy? We mean we are an experimentalist. And so what energy? Because here we are in a curved space-time, there are many energies. It depends where we are. So we are the experimentalists, the brains are here, and I'm here at infinity doing some experiment far away from the brains. Right? So the energy I want to consider is the energy of the observer at infinity. Right? So let's do the following exercise. Let's suppose this is infinity, and we are here. Right? And we want low energy. Right? We want to see low energy. What do we see if we want to see low energy? First, we see this. We see flat space supergravity. But what else do we see? So for that, let's imagine, let's remind us that we see that, let's suppose that we have a friend here that is carrying some very energetic thing. Right? Some huge energy. Right? It's a box with an atomic bomb, I don't know, something very, very energetic. And then this person is going to walk close to it's going to walk far inside, close to the D branes. So we stay here, and he or she is going to go far away. And eventually, they reach here, are very small. Now, what do we see? What I'm representing is what we see here at infinity. So let me put in blue, and let me put this explosion in blue. That's the energy that I see nearby. And now, what do I see when I'm looking at this and seeing what energies are they carrying? Now, for that, let's remember that we have, if I look at my line element, for me, my delta time square measured by observer at infinity is equal the metric to the proper distance at infinity, that it's just ds square, right? My proper time. But here, close to the D brane, when I'm close to the D brane, time gets shifted by R over L. Right? So delta T at infinity is equal to R over L times delta T, the proper time for the proper time for the observer close to the difference. Right? So what he sees as 1 second, I see as if it's 1 second for him, for me it's much less than 1 second. Right? There is this R over L. And so right.
That R is the place of the person near.
No. Sorry. There's something wrong here. Proper time. No. Sorry, I'm wrong. It's the opposite. It's -1 here. L over R. Right? Because the time at infinity is dt. Right? And the proper time is R over L times dt. And so the proper time, right, which is ds squared, is L over R times the time at infinity. I was worried. Yeah. So 1 second for him takes a long time for me. And in particular, the energy measured by me, it's the inverse, right? Time and the energy are conjugate, would be R over L times the proper energy. Now, someone carrying the box with this atomic bomb is close to the atomic bomb, right? Locally, I'm walking with my atomic bomb. I always see my atomic bomb, right? Locally, for me, I mean, there's the equivalence principle, right? For me, I'm always seeing my atomic bomb. So the proper energy for me that I'm carrying the atomic bomb is always the same. But for me that stays here at infinity, this is becoming dimmer and dimmer. And eventually, for me, this atomic bomb is low energy. So for the observer at infinity, anything happening close to the brains is low energy. Right? So for him, anything near the brains is low energy. And so finally, we conclude that for the observer B, at low energy, we get anything, which means I have this background near the brains. So I have AdS5 times S5, everything, not just the lowest modes, not just gravity, but everything. So AdS5 times S5 superstring theory. The full theory with all possible massive strings, everything, black holes, everything you want in AdS5 times S5. Or, that's one option, or I have 10-dimensional supergravity. And the claim is that as before, they decouple. You have either this 10D supergravity or you have AdS5 times S5 superstring. Now, why would they decouple? So now here we can remind ourselves what happens if I put some strings moving in AdS5 times S5. Right? So I have this near geometry, which is AdS5 times S5, and I put a bunch of stuff there. And now you remember from the tutorial, AdS5 times S5, this geometry is like a box. Things don't get out, right? So things, if you put them there, you can throw them away and they go and they bounce back. So things that you put inside AdS5 times S5, this space-time, which we can think as this cylinder, the inside of this cylinder, is effectively like a box. That if you send some closed strings, they move and they come back and they oscillate here, but they don't get out. And so whatever you put here inside this box stays inside the box. And that's how you don't need to take these things and mix them with the stuff far away. Equivalently, you can ask, what about low energy degrees of freedom here? Would they interact with the stuff here? And the answer is again no, because low energy stuff here will have a very long wavelength, and this AdS is like a box, and so it's like measuring some microwaves with your radio antenna. So what happens is that the absorption cross-section for stuff from outside to go inside decays with the frequency, and it will fade away. And so in practice, you have this decoupled system. So they decouple again. Because stuff inside the box stays inside the box, and long wavelength stuff outside the box is not absorbed by the box. And so we conclude that this is another low energy description of the same stack of d-branes. And now we can equate A and B there. And if we equate A and B, you conclude that 10D supergravity shows up in both sides. So you can basically, if you equate both, you can cross them out. Huh? You equate both A and D, you just cross out 10D supergravity. And we conclude that 4-dimensional n equals 4 super Yang-Mills, the full theory, is equal to type 2B 10-dimensional superstrings in a 10-dimensional background, which is AdS 5 times a 5 sphere. And this is AdS, and this is the CFT, and this is what is called AdS CFT. So next time, we will make a few comments about this duality, about how the matching of parameters go, and we'll try to make one check of this duality. It's a conjecture. It's not a proof, because what I told you is cannot be seen as a proof. I mean, there were many steps that were kind of hand-wavy, right? Like crossing gravity out and stuff like this. It's kind of, but it leads to a very precise prediction, right? This sum string theory is not a random string theory, right? It's really type 2B in AdS 5 times S5. And so it says that these energies are not any energies. These are energies of strings in AdS 5 times S5. And whatever I compute from the gauge theory, I should be able to compute from the string theory and vice versa. Now, it's going to be a challenge because this theory is easy when the coupling is small. This theory is easy when the coupling is large. Because coupling large here means you have an AdS with a big curvature. You have a big radius AdS. You have like a big sphere and a big hyperboloid and small strings moving there. That's easy. But here it's easy when lambda is small. That would correspond to a very curved AdS where the strings are huge, and so strings would be hard. So when this theory is easy, this is hard. When this is easy, this is hard. So that's a curse and a blessing. It's a curse because it's very hard to check if it's true. Because when you can compute something here, you cannot compute there, and vice versa. But you can say it's a blessing because it allows you to compute things that you could otherwise never compute. Because if you really trust the duality, you can compute things here that are telling you something trivial here. It's telling you about very quantum strings here. And something trivial here, it's telling you about strongly coupled quantum field theory. So we have to see it both ways, and that we are going to start with some comments about how we can think of AdS CFT next in tomorrow's last class, and then we'll try to do a check and about can we do some non-trivial check that is not just symmetries but really dynamics that would say, wow, it's impressive. We believe probably this is okay, and that's what we are going to do next time. Okay.